This is Mr. Anderson from Kellogg Community College for Math 121. We're going to be looking at Section 4.3, Chapter 4, Section 3, Absolute Value Equations and Inequalities. The absolute value notation is two straight lines on either side of the variable. And the definition is going to be, roughly, it's the distance from zero. As earlier in this book, we have showed that the absolute value of -4, its distance from 0 is 4, but the absolute value of a positive number, like 8, will also be 8. Notice that it does not turn any number into its opposite, it merely measures the distance from 0. Now, what we're going to do is we're going to solve an equation using absolute values. I've written out your two-step process for solving when things are absolute values. The first thing you're going to do is solve it like you see it, which means that you're going to solve the equation for when x is equal to p. So here's my equation. Solve it like you see it without the absolute value symbols, and that's one of your two answers. Secondly, you're going to solve for the negative answer. You might need to flip the symbol too if this is an inequality. So your second step would be to take your x and take the negative answer, whatever that answer was, and solve for that. And since there is nothing to do in terms of solving this one, you're going to have your answer set of -10 and 10. Because if I plug either of these values in for my x, that would give me an answer of 10. Please note that the absolute value of a number can never be a negative, so this is impossible. There would be no solutions to this because there's no number you can ever plug in for a variable x to get a negative answer. Alright, moving on to a couple of the examples here, following my rules. Okay, the first one is to take this and figure out what values of x I could plug in there to make this equation true. So the first thing I need to do is I need to solve it like I see it. 5x plus 2 equals 7. Subtract 2 from both sides. 5x is equal to 5. Divide both sides by 5. X is equal to 1. This is one of my two answers I will have for the problem. Then I'm going to take my answer, take my original problem, and solve it for when it's equal to -7. Now, you would flip the symbol if this is an inequality, doesn't really matter with an equal sign, and we solve for x again. 5x is equal to -9. Divide both sides by 5. X is equal to -9/5, or if you want to be fancy, -1 4/5. So my two answers for the problem are -9/5 and 1. And this is my finite set builder notation here, where I have my two numbers that I could plug into my x to give me that answer. Now sometimes you have to modify the problem a little bit before you set up your two different solutions. So here we have the absolute value of x is equal to 5. And without showing the work here, I'm going to have either x equals 5 or x equals -5 and build my notation here. So my answers are from small to large, -5 and +5. Some of the problems further on in your homework sets are going to be worded or shown a little differently. So take a look at this. This is saying let f of x is equal to the absolute value of 2x minus 4 and find all x which this is true. So what they want you to do is they want you to plug that 10 in right here. And I'm going to rewrite the problem using the symmetric property like so. Now the absolute value of 2x minus 4 equals 10. I do the first problem like I see it. Add 4 to both sides. So 2x is equal to 14. Divide both sides by 2. X is equal to 7 as one of my two answers. My second answer is going to be 2x minus 4 equals -10. So I'm going to move that 4 to the other side. 2x is equal to, this is going to be -6. Divide both sides by 2. X is equal to -3. So my solution set is going to be the numbers -3 and 7. If you plug these back into the equation, you would see that they would actually give you the two answers. Let's do that mentally. 2 times -3 is -6. Negative 6 minus 4 is negative 10. The absolute value of negative 10 is 10. I can plug my 7 into this. 2 times 7 is 14 minus 4 is 10. The absolute value of 10 is 10. Way to check your answers. Now, in the same vein as the previous problem, you'll notice that this f of x equals 1 is we're going to have to solve for x using this equation 1. So I'm going to go for my first equation, 3x plus 4 divided by 3 equals 1. To solve for this, I would multiply both sides by 3. That would get rid of the 3 in the denominator. And that simplifies. So I have 3x plus 4 equals 3. Now I'm going to subtract both sides by 4. 3x is equal to negative 1. Dividing both sides by 3, sorry I ran out of room down there, x is equal to negative 1/3. This is one of my two answers. For my second answer, I'm going to, whoops, wrote the wrong number. I'll do 3x plus 4. Oh, sorry about my sloppy penmanship. That's 3x plus 4 divided by 3 is equal to negative 1. I'd multiply by negative 3 on both sides, just like I did in the previous problem. 3x plus 4 equals negative 3. Subtracting the 4 from both sides, I'm going to get 3x is equal to negative 7. Dividing by 3 on both sides, I get x is equal to negative 7/3. So I've got negative 1/3 and negative 7/3, so my solution set is going to be negative 7/3, which is further away from 0 than negative 1/3. And I could plug these back into the equation and see that that would give me an answer of 1. Now the problems get a little bit trickier. Let's go to the next page. Now for this problem, there's a very good explanation in the book about why this process works. But when you have two absolute values equaling each other here, what's going to happen is that you're going to have to solve for when x minus y is equal to x plus 6, and you'll have to solve when x minus y is equal to, in parentheses, negative x plus 6. So again, it's like the previous problem. You solve it like you see it, then you solve it like the opposite of the right. And the book goes into a pretty good explanation about why just doing these two will actually cover all the different situations for the absolute values. But something happens in the first step here. If I try to subtract the x's from each other, what happens is I get a negative 9 equals 6. Well, this doesn't produce an answer. So this is one problem which will only have one correct answer. So in this consistency, we actually have to go check the other case to see if it's possible. So this is x minus 9 is equal to negative x minus 6. I'm going to add x to both sides. So I get 2x. I'm going to add the 9 to both sides just to move that to the right in the same step here. This is going to be 2x equals 3. Divide both sides by 2. X is equal to 3 halves. So my solution set is just 3 halves. So if I plugged 1.5 into this equation, you would see that 1.5 minus 9 is the same as x plus 1.5, or absolute value of negative 7.5 is equal to the absolute value of positive 7.5. And this is the only solution that would work. So they'll have a couple problems like that in your homework. Now, the last piece, which can be a little bit troublesome, is when dealing with inequalities. Now, you have to consider that the less than symbol means and, or intersection, and the greater than symbol means or union. So, just like the first two steps here, you're going to solve the problem like you see it, so x is less than 5. And then you're going to solve for the negative answer, and note that you have to flip the symbol. So you're going to have, since this is a less than symbol, let's put and in here, and it might be good to indicate that at the beginning, of your problem. So x is less than 5, and x is greater than negative 5. Now, before you write your answer set, it's probably a good idea to graph. And this is where the finesse of the problem is going to come into play. I want a number that's less than 5, so this is going to be a parenthesis, from 5 going to negative infinity. But wait, before I get finished here, I also need numbers that are greater than negative 5. So here's a soft parenthesis going in the other direction. These two are going to meet, and when they meet, they fill up this section together. So my solution set is going to be where x is between negative 5 and 5. Notice that this is like the domain problems we did back in chapter 2. Now, it's true that these both graphs overlapped and went continuously in that direction and that direction, but we're looking for this AND condition where it's less than negative 5 and greater than negative 5. Check the problem below it. Here's another AND problem. AND problems are going to look like this in your solution set. So let's go, for most of the time, so let's go take a look here. We are going to solve the problem like we see it. X minus 1 is less than 3. So you move the 1 to the other side, so you get x, which is less than 4. And we're going to have x minus 1, which is greater than negative 3. Move that to the other side. X is greater than negative 2. So it's probably best to graph it so we can visually see what we're talking about here. We want a number that's less than 4. So this is a curve parenthesis right there. And the arrow is going south, and we want x greater than negative 2, so another curvy parenthesis, x going north here, and you see that AND condition means it has to be between this smile right there. So this is going to be the solution set where x is between negative 2 and 4. Notice I use my less than symbols in that direction. The notation has to be perfect here. There's no variation from this notation. Okay, moving on to the last couple problems here. All right. Now before we break this into two equations, it's best to do a little simplification first. We're going to subtract 5 from both sides, and this is going to be the absolute value of x plus 4 is greater than 5. Now we do our two problems. Problem number 1, draw it like I sees it. X plus 4 is greater than 5. Move the 4 to the other side. X is greater than 1. Now we're going to go x plus 4 is less than negative 5. Subtract the 4 from both sides. X is less than negative 9. So I've got these two problems right here. And let's see here. Yep. Just making sure that I'm not making any simple mistakes. Alright, so I'm looking for an x. Now since this was a greater than problem, this is going to be an OR problem, which means I want greater than x greater than 1 or x less than negative 9. So let's go to our graph and see what that looks like. Okay, so we're going to have x greater than 1, so this is going to be a curvy parenthesis that's going to go greater than 1. And we're also going to have 1 at negative 9. It's a curved parenthesis at 9, like that. Now, since this is an OR, we can have this kind of separate intersection here. So my set notation, for one of the first times here, is going to have an OR in it. So x is less than negative 9, or x is greater than 1. Alright, so we've seen that there, and that will help out a little bit. Oops, excuse me a second. Alright, so moving on to the next problem. Moving on, this is going to be an AND problem here. And since it's an AND problem, let's see how we work this out. We want to know that negative 12, we're going to move that to the other side to get this to work out. So we're going to plug that in and go, let's see, negative, the absolute value of x minus 5, and 9 minus 12 is going to be negative 3. Now, let's keep going here. We're going to divide both sides by a negative, so x minus 5 is less than or equal to positive 3, but we got to flip the symbol here. And we got to flip the symbol so that changes it in this direction here. And once we change the symbol's direction, and this is what we're left with, this is no longer an AND problem. This problem that we've simplified x minus 5 is greater than or equal to 3 is now an OR problem. So what started out as an AND, through our manipulation, turned it into an OR. Now this makes it kind of nice. We're going to take our x minus 5 is greater than or equal to 3, and we're going to move the 5 to the other side, and which makes an 8. The symbol does not flip because all we did was move the 5. Then we take our x minus 5, which is, notice the symbol flip, negative 3, move the 5 to the other side, x is less than or equal to negative 2. And here we go, drawing the line. Now we're going to see where this goes. We want a number that's less than negative 2, less than or equal to negative 2. So this is going to be a hard bracket going to the left from negative 2. This is going to be a bracket going to the right from 8. And since this is an OR problem, we're okay. So let's go connect this together here. So we want x. So x is either less than or equal to negative 2, or x is greater than or equal to 8. So if we plug either of these problems into this original function up here, like if we plug a negative 3 in for x, or if we plug a 10 in for x, either condition will give us the answer that we want, which is less than or equal to 9. Now these last two problems are a little tricky. And they're a little tricky because what's going to happen is that we're going to have a little manipulation before we start the problem. So the absolute value of x plus 2, when will it be less than negative 2? Now here's the problem with this. When will it be less than negative 2? Can we ever have an x value which will be less than a negative number? Now what's interesting about that is that you might have to check yourself here a little bit, because you can never ever have a number that's less than a negative number. That's going to be a problem. But since there is a variable here in this situation, you'll notice that maybe there can be. But here's the thing. Once you take the absolute value here, this will always be positive. And a positive number will never ever be less than a negative number. So there's no solutions here. So anytime you get to a situation where an absolute value is less than a negative, it's going to be false. It's going to be an inappropriate equation. Taking a look at this example here, let's look at this one down below. If I subtract 12 from both sides, like I did in the problem above, notice the symbol is not facing in the same direction. This is asking, when will my absolute value be greater than negative 2? Well, no matter what we plug in for x, we're always going to get a positive answer. So when will a positive answer be greater than negative 2? Well, always. So for any real number that we plug into x, this is always going to be true. So whenever you see your absolute value set up across from a negative number, check your two rules here. Does it make sense that an absolute value will ever be less than a negative number? No, it won't. Will it make sense that an absolute value will always be greater than a negative number? Yes, it will. So there is your answer for the problems. So thank you very much for watching. Email me if you have any questions.